So, good morning, dear students. Welcome you all to the module 3. So, in this module, we are going to discuss about freezing depression in freezing point. So, before going to see what is meant by depression in freezing point, so one should understand the definition of freezing point. So, it is the temperature at which the liquid and the solid states of a substance are in equilibrium with each other. So, for a particular substance, the at particular temperature, if the liquid as well as solid states of that substance are in equilibrium, then we can call that temperature as freezing point. And we can also define the freezing point in terms of vapor pressure, the temperature at which the liquid and the solid states of a substance have the same vapor pressure. So from this definition we can clearly understand that the freezing point of particular solvent will be lowered by the addition of non-volatile solute to the solvent, as the vapor pressure of the solvent also lowered due to the addition of solute. So hence the depression in freezing point delta Tf equals to T0 minus Ts. So where T0 is the depression freezing point of the pure solvent and Ts is the freezing point of the solution. And this we can clearly understand by plotting the graph between the vapor pressure and temperature. So by observing this vapor pressure temperature curves, we can get the relation between vapor pressure as well as freezing point. So for this we'll take three different kinds of solutions. One is a solvent, a pure solvent, and second one is solution 1. We can get this one by adding some x grams of solute to the solvent, and solution 2 we can get the solution 2 by adding some y grams of non-volatile solute to the pure solvent. And for the pure solvent we'll get a curve like this, that is AB, and this at point B, so both the liquid and solid states of a particular this solvent is in equilibrium. So at this point, if you extend to the x-axis, we'll get the freezing point of this substance. And if you extend to the y-axis, we'll get the vapor pressure of the that pure solvent. After addition of some x grams of non-volatile solute to the solvent, then we'll get a solution 1, and the curve for the solution 1 will be like this df. So at this point also, at this point means at T1, at this temperature, both liquid and solid states have the same are in equilibrium, or they have the same vapor pressure, that is P1. So if you observe this one, the freezing point of the solution 1 is drops to T1, and also vapor pressure of the solution 1 also drops from P0 to P1. Means this is a lowering of vapor pressure for after the dissolution of non-volatile solute to the pure solvent, as well as the lowering of temperature or depression in freezing point after the addition of non-volatile solute to the pure solvent. And the same thing we can also observe in the case of solution 2, that we can get by adding some y grams of non-volatile solute to the solvent. So this is the curve SJGC. So at point C, the both solid and liquid states are in equilibrium, or they do have the same vapor pressure at this temperature. Means this is the freezing point of solution 2, and the corresponding vapor pressure is P2. So it is still drops, or it still decreases than the solution 1, and even the freezing point also still decreases than the solution 1. So that is T2, and the vapor pressure is P2. So based on these curves, we can get the relation between this depression in freezing point and lowering of vapor pressure. So for that, we'll take these similar triangles BEF and BHC. So from these two triangles, we'll get the relationship like this. Delta TF is directly proportional to P naught minus P. So we can clearly say that the y-axis, that is on x-axis, we have EF upon HC is equals to BE upon BH. So EF refers to T0 minus T1 and HC refers to T0 minus T2. So that is equals to next one BE refers to P0 minus P1 and BH refers to P0 minus P2. So that we get the general relationship between the depression in freezing point and lowering of vapor pressure. That is, they are directly proportional to each other. And now coming to the determination of molecular weight from the depression in freezing point. We can calculate the molar mass of the solute by using depression in freezing point. So we already know that according to Raoult's law, the relative lowering of vapor pressure is equals to weight by molecular weight of solute into molecular weight by weight of solvent. Then we can rearrange this equation as lowering of vapor pressure is equals to weight by molecular weight of solute into molecular weight by weight of solvent into P naught. So in the above equation, the molar mass of the solvent also constant, because if the solvent is there means throughout the experiment the solvent will not change. That's why molar mass and also its vapor pressure, that is P naught, also kept constant. Then the equation, above equation, becomes P naught minus P is directly proportional to weight by molecular weight of solute into 1 by weight of solvent. So then by based on the temperature, vapor pressure, temperature curves, and from according to Raoult's law, we'll get these two equations. And in the third equation, we can substitute the delta TF value in place of P0 minus P. Then we'll get the equation, that is depression in freezing point is directly proportional to this one. Or if you remove the proportionality by using some constant, then delta TF equals to Kf into weight by molecular weight of solute into 1 by weight of solvent. So where Kf is constant, that is a freezing point constant or cryoscopic constant or molar depression constant. If the remaining part, that is weight by molecular weight of solute into weight of solvent, remains equals to 1, then that is molality of the solution equals to 1, then delta TF is equals to Kf, that is freezing point constant. And here we can clearly get the relationship between depression in freezing point and molality, that is delta TF equals to Kf into M. So if the number of 1 mole of solute dissolved in 1000 grams, then we'll get this kind of relation. If weight of the solvent is given in grams, then the above equation becomes delta TF equals to Kf into weight by molecular weight of solute into 1000 by weight of solvent. So if you rearrange this equation in terms of molar mass of solute, that is M1 is equals to this equation, Kf into weight of solute into 1000 by delta TF into weight of solvent. So already we know all these parameters in the above equation. Delta TF means depression in freezing point. Kf is molar depression constant. W1 is weight of solute in grams. W2 is weight of solvent in grams. And M1 is molecular mass of the solute. And Kf also, it is a characteristic of particular solvent, and it mainly depends on the latent heat of fusion as well as its freezing point. So the relation between freezing point and this freezing point constant Kf is equals to RTF square upon 1000 into LF. And in the first module itself, we clearly known that all these colligative properties are related to each other, and we can get the relationship between depression in freezing point and relative lowering of vapor pressure. So from this depression in freezing point equation, we can substitute in place of number of moles of solute, that is W upon M1, and number of moles of solvent N2 is W2 by M2, and we can get the weight of solute, that is W1 is equals to N1 into M1, and weight of solvent W2 equals to N2 into M2. So in this equation, in the depression in freezing point equation, so we can substitute W1 by M1 in as N1, that is number of moles of solute, and in place of W2 we can substitute the number of moles of solvent into molar moles of the solvent. Then equation becomes delta TF equals to KF into 1000 into N1 upon N2 into M2. So if you take both number of moles of solute and solvent aside, then the equation becomes Kf into 1000 by M2 to N1 upon N2. So from our Raoult's law for very dilute solutions, we already derived in the previous modules, that is P naught minus P upon P naught equals to number of moles of solute to the number of moles of solvent. In the above equation, if you substitute the number of, in place of number of moles, the relative lowering of vapor pressure, then we'll get the equation like this. So this is the relationship between depression in freezing point and relative lowering of vapor pressure. Thank you.